In the last couple of videos, that was video number 360 and 361, we looked at using Haworth projections to illustrate the stereochemistry of cyclic hemiacetal monosaccharides, such as the cyclic form of D-glucose. In this video, what we are going to do is apply the information that we learned in those last two videos towards solving some applied problems. This video assumes that you have already viewed the two leading up to it, so we won't be going into the basics here, but instead we'll be applying those basic principles towards solving the problems herein. Let's go ahead and oriented upward in the Haworth and get started by taking a look at this problem. So here we have the structure of D-galactose provided to us. We could also have looked that up on a reference chart of standard aldohexoses. Based on the Fischer projection that we see below, we're asked to draw the structure of beta-D-galactopyranose as a Haworth projection. Let's apply what we learned previously about Haworth projections in the earlier video to go ahead and take care of this. D-galactose, by the way, is an interesting molecule because it is a diastereomer of glucose, and the way that it is a diastereomer is the configuration differs at carbon number 4 of the chain. So here's carbon 1, 2, 3, 4. The only difference between glucose and D-galactose is that the OH here and the H have flipped from the OH being on the left to the OH being on the right, making D-galactose a diastereomer of D-glucose. The implications of that biologically are pretty interesting, in that the molecule galactose is a little bit less sweet than glucose, and it is also unique and interesting in that it links with glucose to form a lactose molecule. We'll get into that reaction in a later video looking at disaccharides, molecules that have two monosaccharides linked together. So with this problem for D-galactose, what we are going to do is draw out our template for a Haworth projection. So we're going to draw the Haworth template for specifically a 6-carbon, or 6-atom, I should say, sugar ring. And we know this is going to be a 6-atom ring because typically when we have 6-carbon atom aldohexoses, in other words, what is most commonly going to form there are 6-membered rings. We also are clued in about this because we have the term pyranose there, and pyranose indicates to us straight away that there are 6 atoms in the ring. So we'll draw the Haworth skeleton of a 6-atom ring. I'll go ahead and do that here in blue. We draw our hexagon shape. The oxygen atom, which will form the ether group of the hemiacetal, is always in this position here in the upper right corner. And then at each of the carbon atoms around the ring, we will draw a line that goes straight up and down from the carbon. And this, at several of these positions, is going to represent chiral centers. Now the carbon at the far right here, where I've drawn the arrow to, is the hemiacetal carbon. That is always where we'll put the hemiacetal carbon. That is also referred to as the anomeric carbon. And this is the position that can be either beta or alpha, because this is the position where a new chiral center forms when we convert D-galactose into the cyclic form through this hemiacetal formation cyclization reaction. And so in the terminology here, beta is defined as having the hydroxy group pointed upward at the anomeric position. Alpha is defined as having the hydroxy group pointed downward at that anomeric position. Since we are asked here to show the structure of beta D-galactopyranose, that indicates to us that we need to place the OH group at the hemiacetal spot here, oriented upward. The other link here would go to a hydrogen, because at each carbon atom around the ring, here, 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 and here, at all of those 4 spots, there will be one H and one OH at each position to allow this to fit the formula of a standard monosaccharide, and also so it'll match the structure that we see here, where each of the carbon atoms is bonded to a hydrogen and to a hydroxy group. So that takes care of our second criteria in drawing Haworth projections, which is that we're going to fill in the beta or the alpha OH group, which is our hemiacetal OH. And you may notice as I'm going through this that I'm not going through steps 1 through 5 in exactly the same order that was used in the previous video, and that's okay. We can go out of order here. The only step that really has to be done absolutely in order is the first step of drawing your skeleton. From there, the other steps can be done in whatever order you are most comfortable with. So step 3 of this, what we will do is specify the D or L configuration, where D indicates that we have a CH2OH group oriented upward at the carbon of the ring immediately connected to the ether group. That is the carbon immediately to the left of the ether group. L indicates that the CH2OH group at that position is oriented downward at that position. And the position that we're talking about, I will go ahead and highlight here in green to match the color that we're using to illustrate point 3. That's the position right here. So this is the carbon on the left of the ether group, right here. And that would represent the carbon atom right here in my schematic, the carbon to the left of the oxygen that forms the ether group. So that's right here. And then we're going to put the CH2OH group upward here, since this is specified as D-galactopyranose. So the D here tells us that we need to put a CH2OH group right there. If you're wondering where that CH2OH group came from in the original acyclic molecule, the open chain form, it came from right here. That CH2OH at the end of the chain is what corresponds to the branch coming off of the cyclic form there. Then in our final step, what we are going to do is fill in the remaining spots. That is, each of these lines that does not yet have a group attached at the top or bottom. We are going to be filling in each of these, highlighted in that lovely light brown color, with either an OH up and an H down, or vice versa. How do we determine who goes where there? Well, OH groups that are on the right in the open chain form, in the Fischer projection, in other words, the structure on the right, the structure on the left, OH groups that are on the right-hand side of our Fischer projection, that is the OH groups over here, will, in the Haworth projection, go below the ring. So they'll be below the ring in the Haworth projection. And then, analogously, OH groups that were on the left in the Fischer projection will be above the ring in the Haworth. So let's take a look at how to sort that out. In order to sort that out, what I'm going to do to keep myself oriented is I'm going to number the carbons of our open chain form here, 1 through 6. This is a hexose, so we expect there to be 6 carbons. If there's not 6 carbons, then we need to go back and recount. And then keep in mind that when we convert the open chain form into the cyclic hemiacetal form, position number 1, which was the aldehyde group to start with, is always right here. The aldehyde group is what becomes the hemiacetal carbon, that carbon that has an OH group and an ether group bonded to the same carbon. Then, going around the chain, we number this way, 2, 3, 4, 5, and 6, representing the 6 carbons that originated from our chain here on the left. You will notice that position number 6 is CH2OH, just as it was position number 6 over here. That's no coincidence. That's due to exactly how this cyclization reaction happens. So keeping in mind the numbering system we've used here matches the numbering system over here, what we can do then is simply look at position number 2 of our open chain form, and seeing that at position number 2 of our open chain form, the OH group is on the right. That means, since it was on the right in the Fischer projection, that it needs to be below the ring in the Haworth projection. So that means that this OH group needs to be below the ring. On the other hand, at position 3 and 4, the OH group is on the left, and the OH group on the left means that the group is going to be positioned above the ring. So let's go ahead and draw that in. At position number 2, we are going to place the OH group below the ring. Hydrogen will be above the ring. At position number 3, here, OH group will be above the ring. hydrogen below the ring, and same thing at position 4. The OH group is above the ring, the hydrogen is below the ring. And with that, we can double check that the structure we've drawn has a complete octet at all of the atoms, meaning at each carbon atom specifically, we have 4 bonds, and we have filled in something at the end of each of those lines. Don't leave any of them empty, because leaving one empty would imply there's a methyl group at the end of that line, and there are no methyl groups in these molecules. So with that, we've satisfied that we have indeed drawn the beta anomer, because we have the beta position at the anomeric carbon there with the OH group pointed up, D, because we have the CH2OH group oriented up, galacto, because we derived this cyclic molecule over here from the galactose molecule on the left, pyranose, because there are a total of 6 atoms in the ring, making it a pyran derivative.